The very first organism we're going to take a look at is probably the one that you're most familiar with, and that is the earthworm. Probably many of you remember digging out earthworms as fishing bait or seeing them on sidewalks after major rainfall events. Earthworms are very common in soils in the Midwest, and we're going to take a look at the role that they play in the soil environment. Earthworms, they are a macroorganism. What this means is that you're capable of seeing it right with your naked eyes. So you don't need a microscope or any other device to be able to see this organism. Earthworms are important because they are able to directly eat organic matter and soil. So they'll actually ingest the soil whole, they'll decompose that organic matter, and they'll produce a lot of waste as an output from eating all of that soil. They're actually able to consume more than a ton of soil per year per organism. That's a pretty impressive number. They are very productive organisms and they will recycle a lot of soil. In the process, they're breaking down that organic residue, they're adding those organic materials and those nutrients to the soil, so they're beneficial in the fact that they can recycle a lot of nutrients. One thing that's sort of important to talk about with earthworms is the fact that they make large burrows. They make macropores. This is great for helping facilitate water and air movement, but does have some concerns that we'll talk about in a little bit. This is an interesting picture. This is actually a picture of earthworm casts. Casts are essentially earthworm poop. As those earthworms are consuming those soil particles, they're producing a waste product, and that waste product is sticky, it's gooey, and it actually glues and binds those soil particles together. If you have an opportunity, take a look at the surface of the soil, and you're going to see, if you can find the earthworm burrows, you're going to see a lot of these earthworm casts right next to the burrows. Earthworms, as we've already discussed in class, are not native to the upper Midwest. During the last glaciation, all of the native earthworm populations were wiped out due to the cooler temperatures, and earthworms are just now making their way back to the upper Midwest as now an invasive species, which means that they're not naturally found here, so they're going to cause some issues. They're not such a problem in agricultural settings. In fact, they're very beneficial because of their ability to recycle so much waste. The problem is when earthworms get into forested settings. Earthworms aren't native to the forests, and what's going to happen is where you have earthworm invasion, those earthworms are going to consume a great majority of the forest floor. On the forest floor, we want to keep that organic matter present. We don't want to decompose it. The problem is the earthworms don't realize that. They decompose the forest floor organic matter, and they break it down far too quickly for the forest to naturally regenerate it. This is a screenshot of a website, the Great Lakes Worm Watch. Because earthworms are an invasive species, not native to the Great Lakes region, there's been a group that's been monitoring these earthworms over time, most of which have been brought to the upper Great Lakes region by fishing bait. It's been a huge problem. Here's some before and after pictures of what a forest looks like before earthworm invasion. You can see a nice dense floor cover. This nice dense floor cover is important for water erosion prevention. It's important for providing nutrients for the trees. It's absolutely essential that forests have a dense floor cover rich with organic matter. However, after earthworm invasion, and these are pictures from the upper Midwest, this is what that same forest floor looks like. Not so great. You can see the entire area has been decimated. Most of the low ground cover has been removed. A lot of those leaves have been decomposed. This really strips the soil of key nutrients that are needed to support this ecological environment, which is a very bad situation. Here's what it looks like in a diagram. In a forested situation, you have a rich organic layer at the surface. When you have earthworms that those earthworms are going to decompose most of that organic material, leaving you with just the mineral surface horizons exposed. The problem with that is that you're going to start to expose those fragile roots, and you're going to leave the tree more susceptible to infections and diseases. It's causing all sorts of issues in the forest floor, which is not a great thing. This was a picture that I just recently took at a soil pit near Plum City, which is just south of River Falls. If you take a look, you can't see the scale. This is actually a centimeter tape. All of these holes here represent earthworm burrows that are present in this soil. And if you look down at the bottom, you can see this sort of long, linear black feature. We're going to zoom in on that, and you can see it right next to my trowel. This long, linear feature here, which is present both right next to the trowel and closer to the bottom, that's actually an earthworm burrow. So what's happened is this earthworm has taken organic matter from the surface and it's brought it lower down into the soil. You can also see the nice macropores that the earthworm has created as well. I love this picture. I took this picture in Ohio a few years ago, and it is also a picture of an earthworm burrow, but the reason that I really like it is that you can still see the slime from that earthworm. So the shininess that you're seeing in the photograph is the slime that the earthworm adds to the soil. That's great for binding soil particles and improving soil structure and water flow, but as we're going to see in a little bit, it can also have some issues. Again, in agricultural settings, we don't have the same problems as forested settings, but we have some other problems that we do need to deal with. Okay, here's one of those earthworm macropores, my thumb for scale. How will this affect water movement? It's going to affect water movement quite extensively. If we think about it, if we were to pour a cup of water on this particular soil particle or soil clod, what's going to happen is that the vast majority of the water is going to take the path of least resistance and just go straight down that macropore. It's not going to fight with the smaller pores, it's going to go straight down that macropore. Some data, if we look at the number of earthworms by corn residue, we see that the greater the amount of corn residue, the higher the number of earthworm middens are just the same things as casts. So the more residue you have, the more earthworms you have. Well, that makes sense because that residue is serving as the food source for those earthworms. We can also see on the other side of this graph, on the y-axis on the right, we have hydraulic conductivity. If we remember back to our unit on soil water flow, hydraulic conductivity represented the ease of water movement through the soil. So if we follow the dotted line, what we also find is that as the number of earthworms increase, the hydraulic conductivity increases as well. That just means that it's much easier for water to flow through the soil because we have all of those macropores that are present. The problem is that water is flowing in a mechanism that we call preferential flow. Preferential flow is the quick, non-uniform movement of water through cracks, root channels, and earthworm burrows, along with some other things as well. So if we were to take a look at a uniform soil without earthworm burrows, if we were to just apply some blue dye at the top and take a face of that soil away, in a uniform soil we would find that the water would go down to approximately a uniform depth. In preferential flow, where we have earthworm burrows, what we're going to find is that much of the water flows straight through that burrow that's present. Because it's large, it has far less resistance, the water's just going to naturally take that path of least resistance. That's what we call preferential flow. Most soils are not uniform. We're either going to have root channels or earthworm burrows. The more earthworm burrows and root channels you have, the more opportunity you have for preferential flow. This is a picture of a dye tracing experiment. The dyes are non-toxic. They're pretty fun to work with. This is actually a meter squared area that's been set up, and the blue dye has been added, and then later they've gone back and excavated the area, and you can see the path that water's taking. We have some, uniform flow at the top, but then towards the bottom you can see that much of the water flow is concentrated in the burrows and the macropores that are presumably created from the earthworms. I love this picture because it shows the direct effect of earthworms. You can see the blue dye, it's following an earthworm burrow, and on this burrow here you can actually see an earthworm coming out. So it proves the fact that yes, indeed, those macropores are being created from those earthworms. The problem comes though when you have contaminants that are being applied at the surface. They're also going to move by preferential flow. This is equally a problem in agricultural and urban settings. In urban settings, we have high rates of fertilizer application with turf management. In agricultural settings, we have pesticide application and we have nutrient applications that we have to think about. Anything that gets applied to the surface, if you have earthworm burrows that are present, it could move by preferential flow. And the problem is that with preferential flow, oftentimes the wetting depth, the depth to which the water goes, is going to be deeper. And when it's deeper, it is more likely to impact groundwater and potentially drinking water. So that can be a huge concern with earthworms. So earthworms have some great benefits. They add a lot of organic matter to the soil. They recycle, they break that organic residue down. But a couple of concerns, especially in forested areas with consuming too much organic matter, and then in areas where we have a lot of burrows contributing to preferential flow and ultimately, potentially, the movement of contaminants.